August 2015, Typhoon Saudalor drives across northern Taiwan, and rain hammers a tower half a kilometer tall. High inside its crown, a steel sphere weighing 660 tons swings free on its cables. That night, it travels about a meter from center, the largest movement ever recorded there. To understand that swinging sphere, rewind. Taipei sits in a shallow basin ringed by green hills, built on a floodplain of soft sediment laid down over thousands of years. It is one of the most livable capitals in Asia. It is also one of the most difficult places on Earth to build something very tall. Taiwan exists because two tectonic plates are colliding. The Philippine Sea Plate grinds northwest against the edge of the Eurasian Plate, crumpling the seabed upward into mountains. The island keeps rising, and it pays for that rise in earthquakes. Thousands are recorded here every year, and a few of them are devastating. Then there is the sky. Taiwan lies squarely in the western Pacific typhoon belt, struck most years by storms that have spent days gathering strength over warm ocean. Gusts can exceed 200 kilometers an hour. For a slender tower, wind is not weather. It is the load that decides the design. In the late 1990s, a consortium proposed a new financial center for Taipei's Xinyi district. Not merely a landmark, but the tallest building in the world. The architect was C.Y. Lee. The structural engineering came from Fortin Tomasetti, working alongside local engineers. The chosen site sat on soft basin soils near the eastern edge of the city. Ground investigations found a fault trace running close to the site. In Taipei, there was no perfect ground, only ground with different problems. So the engineers accepted the land they had and set out to design for the worst the island could reasonably deliver, in wind and in shaking, for a structure meant to last centuries. Here is the bind at the heart of the project. Earthquakes punish mass, because the heavier a building, the harder the ground can throw it. Wind punishes flexibility, because the more a tower yields, the more it sways. Solve one and you worsen the other. This tower had to answer both at once. The form answered a cultural brief as well as a structural one. C.Y. Lee stacked 8 flared modules of 8 floors each, so the tower widens as it rises, like a segment of bamboo or a tiered pagoda. In Chinese tradition, 8 signifies prosperity. The shape also gave engineers something useful. It broke the building's silhouette into repeating tiers. Beneath the glass, the skeleton is simple in principle. A braced steel core runs up the middle. 8 enormous columns stand at the perimeter. Every few floors, deep outrigger trusses tie the core to those outer columns, so the whole cross-section resists bending together rather than the core fighting the wind alone. It begins far below ground. Around 380 piles were bored beneath the site, driven roughly 80 meters down and socketed about 30 meters into the bedrock underlying the soft basin fill. Each is designed to carry on the order of 1,000 tons. The tower does not rest on Taipei's mud. It grips the rock beneath it. Above the piles, the engineers laid a thick concrete mat, spreading the tower's immense weight across the ground like a raft. 5 basement levels were carved out beneath it, and the walls of the pit had to be held back while the city carried on around the site. The building's hardest work was finished before it appeared. Then came the steel. The frame uses high-strength plate welded into enormous box sections, fabricated to fine tolerances and lifted into place piece by piece. Some individual columns are so large that a person can stand inside them before they are closed and welded shut. Every joint had to be inspected, because everything above depends on it. The 8 perimeter mega-columns were then filled with high-strength concrete through the lower 2/3 of the tower. Steel gives toughness and the ability to bend without breaking. Concrete gives stiffness and sheer weight to resist. Together they form composite columns far stronger than either material working alone. At intervals up the height, outriggered trusses were installed, story-deep steel frames reaching from the core out to the mega-columns. When wind pushes the tower sideways, these trusses force the outer columns to resist too. One side pulled down, the other pushed up. The building fights back with its full width. Meanwhile, in a wind tunnel far from Taipei, scale models of the tower were tested in artificial storms. Engineers were hunting a specific danger. As wind flows past a tall building, it sheds swirling vortices alternately from each side, and those vortices can shove the tower rhythmically, side to side, in time with its natural sway. The fix was geometry. The corners of each flared tier were stepped and notched rather than left sharp, so the airflow never organizes into one clean rhythmic pattern. Confuse the vortices, and you cut the sideways force substantially. Testing showed the shaped corners removed a large share of the wind load before a single ton of steel was added. By 2001, the tower was climbing fast, a bright frame rising over the low roofs of Xinyi. Cranes climbed with it. Steel arrived by night, when the roads were clear. From the street, people could watch the city's new horizon assemble itself, one 8-floor module at a time. On the 31st of March, 2002, a magnitude 6.8 earthquake struck off Taiwan's east coast. The unfinished tower swayed. 2 tower cranes tore loose from the upper structure and fell. 5 people were killed. It was the worst day of the project, and a brutal reminder of where they were building. Work stopped. Engineers surveyed the structure and found the frame itself sound. The failure had been in temporary equipment, not the building. Construction resumed under revised procedures. The tower would carry on rising, but the earthquake had made the abstract concrete. This ground moves, and it does not warn you. There remained a subtler problem, one the structure alone could not solve. The tower would not fall in a typhoon, but it would move. In a long storm, the upper floors would sway slowly back and forth, and people inside would feel it. A queasy, endless drift that empties offices faster than any structural worry. So, the engineers added a counterweight. The idea is old and beautifully simple. Hang a heavy mass from the top of a swaying structure, tuned so it swings at almost the same rhythm as the building itself. As the tower moves one way, the mass lags behind and pulls the other. The mass they built is a sphere of steel, about 5.5 meters across, weighing 660 tons. It was assembled in place from dozens of thick steel plates, stacked and welded together layer upon layer, because no crane in Taipei could have lifted the finished ball into the crown of the tower. It hangs from the 92nd floor on 8 steel cables, dropping several stories through the building's crown. Beneath it sit 8 hydraulic dampers, thick pistons that convert the sphere's motion into heat and bleed the energy away. A heavy steel ring below acts as a bumper, catching the ball if a storm ever pushes it too far. In a storm, the effect is undramatic and completely decisive. The tower leans, the sphere trails a beat behind. The cables pull the building back towards center. Reported figures suggest it cuts the tower's movement by as much as 40%. Nobody in the offices below sees it. They simply feel a building that stays still. The Great Sphere protects the occupied floors, but the 60-meter spire above them has its own problem. A slender mast can flutter in wind that the main tower barely notices. So a pair of much smaller tuned mast dampers was installed high in the pinnacle, doing the same job at a different scale. Then the designers did something unusual. Rather than hiding the damper in a machine room, they built the observatory around it. Visitors ride to the upper floors and stand beside the sphere, watching the cables and the pistons. A piece of structural engineering became one of the building's main attractions. Getting people up there needed records of its own. The tower's express lifts were at opening the fastest passenger elevators in the world, climbing at around 1,010 meters per minute and reaching the observatory in roughly 37 seconds. The cabins are pressure controlled, so ears do not suffer on the way up. On the 31st of December, 2004, Taipei 101 opened. 508 meters to the tip of the spire, 101 floors above ground and 5 below. It took the title of world's tallest building and held it until Burj Khalifa opened in 2010. The tests came anyway. Earthquakes have shaken the tower repeatedly since it opened, and the typhoons return every summer. In 2015, Saudalor pushed the damper to its record swing of roughly 1 meter. Engineers watched the numbers. The structure behaved as the models had predicted it would. Not every question was settled. One Taiwanese geologist argued publicly that the tower's enormous weight might have stressed the ground and influenced local seismic activity. The claim was contested by other researchers and has never been established. It lingers as a reminder that a building this heavy is itself a geological event. Years later, the tower was refitted for efficiency and certified as one of the greenest tall buildings in the world. But its lasting lesson hangs in the crown, a ball of welded steel on 8 cables, doing nothing at all until the wind rises. Somewhere above the city tonight, it is waiting. When the next storm comes, it will move first.